Okay, chapter 5 is about proving using the fundamental identities. So first I'm going to show you why some of these identities work. So if we think about our unit circle, remember it all goes back to the unit circle. Make that a little bigger. And we think of a random point on the circle. That's the point x comma y. And I make a triangle out of it, a right triangle touching the x-axis like always. Remember, the unit circle has a hypotenuse, well, a radius of 1, which is the hypotenuse in this case. Theta is between the x-axis and your hypotenuse. This is clearly x and this is clearly y. Well, for right triangles, we already know the Pythagorean theorem. X squared plus y squared equals 1 squared, or x squared plus y squared equals 1. But we also know from our unit circle that instead of x and y, I could call this cosine theta comma sine theta. So I could replace every x with cosine theta and every y with sine theta. And it would still equal 1 because I'm just substituting. And then the way we square sines and cosines, instead of using parentheses like that, we put the parenthesis on the cosine. But it does mean what you see there. You would take the cosine of theta first and then square that answer. This right here is our first fundamental identity. This is cosine squared plus sine squared equals 1, our Pythagorean identity, if you want to call it that as well. From there, I can get the other three that you should be looking at. You should get a cheat sheet, is what we're going to call it, of formulas, and these should be on that sheet. If I take that exact same equation, which I just proved to you as true, and I just do some algebra to it, let's see what happens if I divide both sides by by cosine squared theta. Divide by cosine squared theta. Sometimes I'll just say cosine squared, but the theta is implied. You always need to write your thetas down. Divide by cosine squared and I get 1. Sine squared over cosine squared is tangent squared, because sine over cosine is tangent. And 1 over cosine squared is secant squared, because 1 over cosine is secant. And this is another one of our identities from the same original one, but I just did some algebra to manipulate it and write it a different way. I can do that again. If I take cosine squared theta, the original identity, and instead of dividing by cosine squared, let's divide by sine squared this time. Everything gets divided. Cosine squared over sine squared is cotangent squared, right? Cosine over sine. That becomes 1, and 1 over sine squared is cosecant squared theta. This is the other identity that we will use a lot in this class. Also, and I'm not going to write every single one of them, but realize each one of these gives you 2 more equations. For the purple one, I'm just going to write it one more time. What if I solve it for tangent squared instead? So minus the 1. This, if I can write it right, is also an identity that might be helpful. So if you ever had tangent squared by itself, you could replace it with secant squared theta minus 1. Or more likely, you would have secant squared theta minus 1, and you could replace it with the much more simplified of tan squared. One more just to show you. Original again. What if I solved it for 1 minus the tangent squared to the other side? Then if I ever saw secant squared theta minus tangent squared theta in a problem, I could replace that with 1 to make it a lot more simple. You can do this exact same thing with the blue equation and the green equation as well. So yes, there's 3 Pythagorean identities, but there's really more than that, right? I mean, 9 if each one has 3 options. So on this page, we have some of those identities that I just proved to you, and some you already know. Tangent is sine over cosine. Cotangent is that upside down, cosine over sine. To do proofs, these are our tips for you. You're going to pick one side to work on. You're only allowed to manipulate or change one side of the proof. The other side will never change. It's recommended that you take the bigger, messier one and you condense it, because it's easier to condense a mess than it is to create one, which is what this says, try to crush, not create. You're going to use any of the identities and any algebra that you know to manipulate the chosen side. Do not touch the other side. You're not allowed to touch the other side, but you need to carry it down. It needs to be an equation, a true equation, every single step of the way. It says if you get stuck, back up and check your work. I'm going to say once, do that once. After that, just start over. There's an infinite number of ways to do these proofs. So if the first method you choose doesn't work, stop trying to find your mistake. You could sit there forever looking for a tiny mistake and just start over. Some things we'll be doing is we'll be adding 0, because you can add 0 and not change the equation. We'll be multiplying by 1, because multiplying 1 by 1 does not change the equation. Sometimes turning everything into sines and cosines is helpful. If you see cotangents and secants and all sorts of different trig in the same proof, changing everything to sines and cosines is helpful. A couple more things we're going to do. Make a common denominator. That says common denominator. Multiplying by the conjugate on top and bottom can sometimes be helpful. And there's a note that it might get ugly before it gets pretty, and you are done with when both sides are identical. Remember how we said don't touch the other side? It's not a full proof until you get, for example, tan x cosine x equals tan x cosine x. It literally needs to match. Okay, so I just need you to know this first example is not a proof. It just says simplify. We're just showing you how we can use these identities to make things a little more simple. So, multiplying 1 minus cosine theta times 1 plus cosine theta. You should recognize that as a difference of squares. That's the same thing as multiplying 1 minus x times 1 plus x, and you should be pretty good at that and know you get 1 minus x squared if you multiply that out and simplify it. It's a difference of squares. Usually we go the other way, right? From 1 minus x squared, and we factor it into the above. You also need to be able to go from factored form to multiplied form, standard form. So if I take 1 minus cosine theta times 1 plus cosine theta and I multiply them together, I will get 1 minus cosine squared theta. Now, look at your identities. Again, hopefully at this point you have that cheat sheet where they're all written on one page. Is there anything we can replace 1 minus cosine squared theta with? So remember over here, in blue, cosine squared plus sine squared equals 1. Well, 1 minus cosine squared, if I minus the cosine squared to the other side of that blue equation, that's going to give me sine squared theta. So we simplified that whole problem down to just sine squared theta. Again, not a proof, but just some ways we can manipulate trig so you can see how it works. Number 2, also not a proof, but how can we change this so that we can simplify it? Well, when I see 1 over sine squared, remember the reciprocal of sine is cosecant? That's the same as cosecant squared theta, minus, what's the same thing as 1 over tangent squared? Well, the reciprocal of tangent is cotangent, so cotangent squared theta. Is there anything on your cheat sheet that we can replace cosecant squared theta minus cotangent squared theta with? So that is the green equation, right? Cosecant squared minus cotangent squared just ends up being 1. So we simplified the original down to 1. Okay, this is the last one where we're just doing algebra. So remember that you cannot distribute a square, right? You cannot just square that and square that. That's not how it works. That kills the puppies. This is sine x plus cosine x times sine x plus cosine x. Maybe you need to make an area diagram to multiply that out, or maybe you can use FOIL. If I haven't taught you FOIL yet, FOIL, the F stands for first. So you multiply the first terms of each parenthesis together. Sine x times sine x is sine squared x. FOIL, the O stands for outer or outside, depending on who you ask. The outer parenthesis of the whole entire problem is sine x times cosine x. You're multiplying always. Cosine, I like to write them alphabetically, but it does not matter. Cosine x sine x. FOIL. The I stands for inner or inside, depending on who you ask. Multiplying the insides together alphabetically gives me cosine x sine x. And again, FOIL. The L, see how it spells FOIL, stands for last. So multiply the last terms in each parentheses. Cosine times cosine is cosine squared x. Then you need to condense. If you're going to use FOIL, that's just the first step. Now you need to combine like terms. I have a sine squared x. I have cosine x sine x and another cosine x sine x. That gives me 2 cosine x sine x. And then I have plus cosine squared. So that's the multiplying step. That's the algebra behind it all. Now you need to look for anything you can replace with your cheat sheet. So even though they're far away, sine squared x plus cosine squared x is replaceable. What does sine squared x plus cosine squared x equal? That just equals 1. And then I have my leftover. And I can't replace that with anything, so this is my simplified form. Okay, now we are finally to the proving part, which is what our essential skill is. I'm just writing the problem over here so I can use the middle of my screen. Make sure you write the problem down correctly. Okay, you want to manipulate the mess. Hopefully you understand that this side, the left side, is more messy, right? It's got more going on than the right-hand side does. So I'm going to use algebra or my identities to manipulate the left side until I get the right side. Remember, the right side, we're not going to change at all. That's going to be written down just like it is every single time. You cannot, like, multiply both sides by 10 or something. You can't change the other side. So, first thing I see, pause the video and see if you see any identities. First identity that I see is 1 minus cosine squared. So I'm going to keep the top. You can only do one mathematical step at a time. What does the bottom become? So 1 minus cosine squared, that's the first identity, and if I minus the cosine squared over, that leaves me sine squared on the other side, and I bring down the cotangent x. If you're not listening right now, you're going to lose points. You bring it down every single time. Okay, now I'm just doing algebra. Everything is being multiplied on the left. Well, if everything's multiplied, a sine x on top crosses out with one of the sine x's on the bottom, and I'll have cosine x over sine x left. One step at a time, bring down the right-hand side every time. Well, cosine over sine is defined as cotangent x. So I proved the proof. Okay, number 5. Go ahead and, well, write it on your paper so you have enough space on each side. I'm probably just going to leave mine where it is this time. And then decide which side you're going to manipulate, which side's messier. Clearly the left side has more going on, so we're going to leave the right side alone. And then we're going to need to multiply that out. So if you want to do FOIL, you can practice your FOIL, or you can do an area diagram. Pause the video and see if you get the same thing as me when you multiply that out. So first, don't forget the thetas. I'm not going to change colors. Outer goes to here. Multiply. Inner, multiply. It doesn't matter what order you write the trigs in. And last, multiply. Don't forget to bring down the other side. Do not not change the other side at all, or you are not doing a proof. Okay, when I see this, I see a ton of different trig functions. So at this point, oh, hey, no one told me. When you multiply -1 times cotangent, you get negative cotangent. Okay. So I'm going to do the change everything the sines and cosines. There's too many different types of trigs. I have no idea what to do with a cotangent next to a secant. That's just a mess. So I'm going to replace everybody with their sine or cosine counterpart. Every trig function can be replaced with something that has sines and or cosines in it. So for example, cosecant. Cosecant is the reciprocal of sine, so I can replace it with 1 over sine theta times. Secant is the reciprocal of cosine, so I can replace it with 1 over cosine. Pause the video and see if you can finish replacing every piece with something that only has sines and cosines in it. Cotangent is cosine over sine. But do not change the right-hand side. Okay. Now that I see them next to each other, the first thing I notice is that this middle-ish term has a cosine on top and a cosine on bottom. So I can cross those out. Write down everything that's left. Since nothing's going to cross out on this left term, I'm going to write them together, right? They can be written together in the bottom. The cosines cross out, and I'm left with 1 over sine theta. Keep the right-hand side there. Do not change it. Well, now that I've crossed one of those out, I see that this is same number but opposite symbol, right? Add, subtract. So those are going to go away. Only one thing can happen at a time. So it's getting closer, it's getting neater. Then, common denominator. So, let me talk you through it. See how on the right-hand side, it's just one term? And on our left side right now, we have 2 terms. Well, the only way to merge terms like that, adding and subtracting, is to have a common denominator. So my common denominator is 1 of everything, right? So this one has sine, cosine. This one only has sine, so I need to multiply by cosine over cosine. That's not changing the equation because I'm doing it at the top and bottom. I'm just making a common denominator. So that's going to be 1 minus cosine times cosine is cosine squared theta over, and now I can write it as 1 fraction because the denominator is common. Then I have an identity. Do you see it? Is there anything on the left that you can replace using your cheat sheet? 1 minus cosine squared. That's sine squared. Then, now that all the addition and subtraction signs are gone, remember you can't reduce when there's an addition or a subtraction sign on the top. But now I have I have 2 signs on top, but one of them crosses out with one of the signs on the bottom. And now I'm down to sine over cosine, which is tangent theta. We've proved it. Okay, number 6. Hopefully you're getting good at understanding, and it's not always the left, it happens to be in this video, but it won't always be the left side, but clearly the left side is more complicated. The right-hand side is much more simplified. I'm going to leave the right side alone, and I'm going to bring it down every single time. For the left-hand side, again, when I look at this, I see that the right side is 1 term. So I want to get the left side to be 1 term. So a common denominator will help me do that, right? Remember, 1 plus sine theta is a term, and cosine theta is a term. So your common denominator needs to have both things. So I need to multiply, the right-hand side is missing a cosine theta. So I'll multiply top and bottom by cosine theta. The left-hand side, just of that one side of my equation, right, is missing the 1 plus sine theta. That says 1 plus sine theta. So multiply the top, leave the bottom in factored form. So cosine times cosine is going to give me cosine squared. I'm making a common denominator so I can write it as one fraction. The common is cosine theta times 1 plus sine theta. The problem says plus 1 plus sine theta times 1 plus sine theta. That's a good time to practice your FOIL or do an area diagram. I'm not going to show it anymore. Pause the video and either do FOIL or an area diagram for that and then check it with mine. You get 1 plus 2 sine theta plus sine squared theta. And it still equals 2 secant theta. Do not change that side. Okay. Now, do you see any identities on the top? The bottom's in factored form. We're going to leave the bottom alone for a minute. The top is kind of a mess. Is there any pieces we can merge together to get rid of replace using an identity? So I see a cosine squared plus a sine squared. They're kind of far apart, but they're definitely there. Cosine squared plus sine squared equals 1. So that part gives me this 1. Then I have the plus 1 that's in red and the plus 2 sine theta. And I still have the over part. I'm not changing that. And I'm not changing this side. Now I can do the 1 plus 1. That's 2. Okay. Now, another thing to notice or think about, sometimes I draw little thought bubbles. While I'm doing this, I'm not changing this side, but I'm thinking of it as 2 over secant is cosine theta, right? So if I can get this to be 2 over cosine theta, then I've done something good. Well, I have some 2's, but I have too many 2's, and I already have the cosine theta. So it looks to me like this 1 plus sine theta is going to need to cross out. Well, if you factor the top, right, GCF, they both have a 2. So if I factor it out front, it doesn't disappear. It gets written out front. When you divide by 2, you get 1. When you divide by 2, you get sine theta. Keep the bottom. Now I have that matching factor. Because it's an entire factor, it crosses out. And I have 2 over cosine theta left, which is my thought bubble, which is equal to 2 secant theta. So we proved it. Okay, last one for today's video. Put it in the middle. This is all supposed to reduce down to be 1. Remember, the plus and minus holds it together, right? You cannot cross out 2 of these signs with 2 of those signs. That's not how math works. If you can't do it with numbers, you can't do it with cosines and sines, right? So like if I had 2, it's minus, I guess, minus 8 over, 4 minus 16. I can't just cross these out and get 2 and cross that out and get 2. The answer is not the same when you do that. So always think about algebra or numbers and whether or not something is legal to do in math. But I do see minus signs. And I do see that the exponents are all even. That means the left-hand side, which clearly that's the side we're manipulating if you haven't caught on yet, is difference of squares. Both the top and the bottom factor as a difference of squares. See if you can factor those. So difference of squares, you square root it. So I'm still going to have sine squared x minus cosine squared x, one with a minus and one with a plus. Over. The bottom is only squared, so that'll be sine x minus cosine x, one with a minus, one with a plus. And keep the other side. Okay. Now that I see this, maybe I shouldn't have factored the bottom, right? If you look at the top of what I just wrote down and the bottom of the original, if I just keep the original, and there's more than one way to do it, look, my factor on top completely matches the factor on the bottom. and I'm left with sine squared x plus cosine squared x. It's supposed to equal 1. Well, this is an identity. It does equal 1. 1 equals 1, and I proved it. So clearly we're going to do more examples in videos and more examples in class of all the different types of things that might happen. But there is not one right way to attack something. One way might end up being easier in the long run, but if you do legal math, right, legit algebra, things that you're actually allowed to do, you can get there more than one way. Okay, I hope this helps, and I hope you guys are doing good.